The last main characteristic of DNA that you're going to want to nail down is that DNA is anti-parallel. And if we go ahead and think about what this term means, if you think about two things that are parallel, they run side by side. If something is anti-parallel, they still have this orientation, but one goes in this direction and the other goes in this direction. And that's exactly what's happening with DNA. So each of these two strands of DNA is still made up of a whole bunch of nucleotides. It's still made up of a whole bunch of the same types of Lego bricks. Those nucleotides made up of a phosphate group, a ribose sugar, and a nitrogenous base. There it is. Okay, so both pieces of this DNA have those building blocks. But if you kind of look at the orientation of the building blocks, if you look at the orientation of the nucleotides themselves, you'll notice that on this strand, you've got the phosphate group, then a sugar, then a phosphate group, then a sugar, then a phosphate group, then a sugar. Whereas on this strand, you've got sugar, phosphate group, sugar, phosphate group, sugar, phosphate group. So they're actually in different orientations. And DNA, when we're kind of thinking about directionality, we always think about it from the 5' to the 3' end. And so this strand is running in this direction, and this strand is running in this direction. Let me go ahead and erase some of my notation here so we can talk about this in a little bit more detail. That terminology there, 5' to 3', you might be thinking, like, where do these numbers come from? They come from what part of the nucleotide has 5 components? Yeah, so the nucleotide's made up of a phosphate group, a ribose sugar, and a nitrogenous base. And the ribose sugar, ribose is actually a type of carbohydrate that contains 5 carbons. And if you're like, what? Don't worry about it, we haven't really talked about that yet, but we will come back around to carbohydrates in Unit 4. And so the 5' to 3' notation refers to the carbons in the ribose sugar. And I'll go ahead and draw one out for you over here. And I'll just also erase my anti-parallel notation here so we can really give ourselves some space. Okay, so we normally are going to have a phosphate group, and I'm going to represent that just by a P in a circle here. And that's going to be bound to a ribose. And I'm going to use abbreviated structure here. So my nodes are going to be carbons. And here is my ribose. And it's got a little oxygen in here. And then I'm not going to draw out the full ring structure for the nitrogen base, so I'm just going to put, NB here for nitrogenous base. And that could either be, an A, a C, a T, or a G. But we want to focus on this ribose sugar right here. Okay, so 5' to 3'. First, let's find all the carbons in here. There are 5 of them. And so we're going to have 1 right here, 2 right here, 3, 4, 5. There are 5 carbons in the ribose. And again, these nodes, you can imagine a carbon is right there. Carbon, 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 carbon. And so 5' to 3' refers to which carbon is in which orientation. The carbon that is touching the nitrogenous base is what we call our 1' carbon. And this notation, like that little thing up there, is a prime. So 1', 2', 3', 4', 5'. So when we say that this strand is 5' to 3', we're saying, okay, we hit a 5' and then a 3', and then it connects to the next phosphate group. And then we hit a 5' and a 3', and it connects to the next phosphate group. Not a 5'. Then we hit a 5' and a 3', 5' and a 3', all the way down. Whereas on the other side, if we use this same rule, if we count carbon number 1, the one that's touching the nitrogenous base here, then our 1' carbon over here is right there. And here's our 2, and here's our 3, and there's our 4, and there's our 5. And so on this strand, we're running from 3 to 5, 3 to 5, 3 to 5, 3 to 5. And so DNA always, no matter what, is going to have one strand that runs in this direction and another strand that runs in this direction. They're always going to have that nice anti-parallel structure where one is 5' to 3' and the other is 3' to 5'. And if we kind of get rid, this slide has a lot of notation with extra atoms in here. If we boil it down just to like general structure, if we imagine our nucleotide looks just like you see here, kind of, there's our 5, I'm not a great artist. There's our 5' and our nitrogenous base. You can actually see the difference in orientation without even having to add the prime notation. So you've got, a nucleotide that's right side up on this end and a nucleotide that's upside down on this end. And for y'all, you don't necessarily have to be, geniuses at recognizing exactly what orientation a molecule is, but you should definitely know that if you see a nucleotide in one orientation, you can assume the other one would be in the other orientation. Or if you know you've got one strand that's 5' to 3', you can guess that the other strand will definitely be 3' to 5'. All right, I'm going to put this question after this video, and this is a really high-level question. If you think back to Bloom's taxonomy, we've been talking about like our PLQs help you to build that base, the remember and understand levels, and then our AAEs and our lectures are helping you to practice with like apply, analyze, evaluate, and our exams are assessing you at the apply, analyze, evaluate levels. This is an evaluation question, and the reason this is an evaluation question is because all of the answer choices are true facts about DNA. We've already spent time talking about just now this, anti-parallel structure, 5' to 3'. We spent time talking about in a previous video complementary base pairing. We laid out that DNA is a helical structure, this kind of double helix here. And we talked about nucleotides being made up of a phosphate, a sugar, and a nitrogenous base. But now I want you to take that information and think about it in the context of DNA as a molecule that codes for life, and the idea that all living things reproduce using DNA. And so you might be familiar with Watson and Crick, who won the Nobel Prize for describing the structure of DNA. And when they first described the structure of DNA, when they first figured out all of these things about DNA, they said, "It has not escaped our notice that the model we have postulated immediately suggests a possible copying mechanism for the genetic material." They looked at DNA, they saw all 4 of these things, and one of these 4 things made them think, oh, I know how DNA copies itself. So go ahead in the question after this video and try to figure out if you can determine which of these 4 things helps us to know exactly how DNA copies itself. And then we'll go ahead and talk more about that in the following video.